In this video, we're going to start to take a look at infinite limits. We've looked at functions graphically, such as y equals 1 over x squared, that have unique behavior around 0. When you divide by numbers really close to 0, we get really big numbers. And so as we approach from the right, we're going up to a very, very large y value, and as we approach from the left, we're going up to a very large y value. And we say that this limit approaches positive infinity. And intuitively, this should make sense, because as we're taking 1 and dividing by a smaller and smaller and smaller number, this is getting bigger and bigger and bigger. And so when we divide by something that's infinitesimally small, we should get something that's infinitely big. Let's continue to look at the same function, y equals 1 over x squared, but let's change our focus a little bit. And let's look as x approaches a really big number, or as x approaches positive infinity. And some functions, like linear functions or some quadratic functions or other polynomials, as x approaches infinity, y just approaches infinity, and so it's nothing all that significant. However, there are certain functions, like this one pictured, as we approach infinity in the positive x direction, we notice that our function starts to level out at y equals 0. And we call that a horizontal asymptote, and we've seen that before back in algebra when we would graph. This function starts to level out at y equals 0 as x gets positively huge. So we say the limit as x approaches infinity is 0. And so we can look at it the same way going to the left and negative infinity, and we say, well, as x gets negatively huge, as we're moving in this direction, what's happening to our y values? Well, once again, our y values are settling down, getting close to 0, but never actually touching 0. And that's important. There is an asymptote here, so it never gets there, but it's approaching 0. So remember, a limit doesn't necessarily say what a function is defined as at a certain x value, but it's saying what is it approaching. So as we approach negative infinity on the x value, we are approaching 0 in the y value. Here's a picture of those two general scenarios previously discussed. When we have a limit as a function approaches some finite value, our function goes off to an infinite value. And so a limit goes to infinity because as x approaches a, y is approaching infinity. The other situation is as x approaches infinity, our y value is settling at some value m. There, and we can see the same picture as x approaches negative infinity. This graph is settling at some y value L. Now notice, in this first situation here, if our limit goes to infinity, that means there's going to be a vertical asymptote. Now, that statement is not reversible. If there's a vertical asymptote, that does not mean that our limit will go to infinity. Our limit could possibly not exist, at least our two-sided limit. If there's a vertical asymptote, typically at least a one-sided limit will go to infinity, but don't reverse that statement. Okay, so if we are going to infinity, if our limit is going to infinity, then we have a vertical asymptote. If, as we go to infinity, our y value is settling at a constant or some number, then that is a horizontal asymptote. Let's look at an analytical definition of this situation here. And suppose we have f and it's defined for all x near a. And if f grows arbitrarily large for all x sufficiently close, but not necessarily equal to a, we write that the limit as x approaches a of f of x is equal to infinity. We can use the same reasoning to say that a function goes to negative infinity as x approaches a, and we just say that the limit of f of x as x approaches a is negative infinity. Now, before you get too worried, you may be reading this sentence at the end that says, in both cases, the limit does not exist. Now, what this is saying is that the limit does not exist and that we don't get the limit of f of x is equal to some value L. Okay, we're getting a non-finite number. We're getting an infinite number. And so in that sense, it doesn't exist. But we will not state that it does not exist. We will state that it goes off to infinity. So we can't give a finite number in which this limit approaches, but we know that it's going to approach an infinite number. So let's take a look at an example. Let's say we have a function f of x is equal to x over x squared minus 1, and that quantity is squared. So if we want to look at the limit of f of x as x approaches 1, and let's look at the limit of f of x as x approaches negative 1. Now both of these we can't put in, and that gives us a 0 in the bottom. However, we can still evaluate this limit and find it by looking at the graph first. If we look at the graph of x over the quantity x squared minus 1 squared, we see that as we approach 1, we are approaching positive infinity from both sides. We have to look at both the left and the right. So as we approach 1 from the left, we go to positive infinity, and as we approach 1 from the right, we go to positive infinity. So we say that the limit of f of x is, in fact, infinite. And likewise, looking at negative 1 from the left and negative 1 from the right, we see that we are approaching negative infinity. So this brings us to our one-sided infinite limit definition. That's saying that we have a function that's defined for all x near a, and x is greater than a. And so if f of x is getting very big or arbitrarily large for all x sufficiently close to a, then we say that the one-sided limit from the right is equal to infinity. And we can do the other side and say that if it's getting arbitrarily small or a very big negative number, then we say approaches negative infinity. And the same thing happens with coming from the left. So if we have x values less than a. These graphs depict what we're talking about here, and it's nothing different than what we've already discussed. We're just looking at it from one side. So as we approach a from the right, we're getting arbitrarily large. And as we approach a from the right over here, we're getting arbitrarily small or negatively huge. And so we say the function approaches positive infinity in this situation, and it approaches negative infinity in this situation. And the same thing goes as we approach from the left. As we approach a, we're getting positively huge, and over here, as we approach a, we get negatively huge. So we say the one-sided left-handed limit is approaching either positive infinity or negative infinity. And so this leads us to a definition of vertical asymptotes, and we alluded to this earlier, that if our two-sided limit or either of our one-sided limits approach infinity, positive or negative, then the line x equals a is called a vertical asymptote of x. So keep in mind, just because we have a vertical asymptote doesn't necessarily imply that all of these are true. It might imply that one of these are true, but what this is stating is that if one of these limits are true, then we have a vertical asymptote. Now let's look at determining these limits analytically. So let's say we have a function f of x is equal to 2 minus 5x over the quantity of x minus 3. And so we want to find the limit of f of x as x approaches 3 from the right, and we want to find the limit of f of x as x approaches 3 from the left. Okay, so first let's talk about the limit as x approaches from the right. So let's think about this here. If we have 2 minus 5x over x minus 3. Now if we just plug in 3, we would get a negative 13 over 0. Typically in the past we look at this and we see, oh, dividing by 0 can't happen, this number is undefined. However, we're starting to define this a little more in terms of a limit. Well, as x approaches 3, we're getting a number that is approaching 0 in here. This is approaching 0. So let's say we have a number really, really close to 3, so a little above 3. So 3.00000001, this is a non-zero number, but it's a really small non-zero number. And we have to ask ourselves, well, is that a positive non-zero or is it a negative non-zero? Well, since we're coming from the right, this will give us a positive number that's really close to zero. So we're approaching zero from the right. Up top, we have a negative number. So we have a negative number divided by a really, really, really small positive number that gives us negative infinity. Because as that approaches zero, that negative 13 divided by a number that's really close to zero is going to become infinitely large. But it's negative infinity because the 13 is negative. We can use this same reasoning to evaluate the limit as x approaches 3 from the left of the same function. And we see that we're going to have a negative 13 once again up top and a 0 in the bottom. But what type of 0 is this? Up top we had a positive 0, or a 0 approaching 0 from the positive end. And I know your brain might be shaking right now thinking positive 0, what is that? All right, well, it's something really close to 0 but on the positive end of 0. And over here, if we're going to number just a little bit less than 3, so 2.999999999, then we have a number that's really close to 0 but on the negative end. And so as x approaches 3 from the left, this is approaching 0 from the negative end. And so this is a negative 13 divided by a negative really small number, and so this gives us positive infinity. So I'd like to end the video by looking at this graph of the function, the quantity x minus 2 over the product of the quantity of x minus 1 squared and the quantity x minus 3. And so you may be able to tell using your algebra experience that we're going to have a vertical asymptote at 1 and 3 because those are the values that give us 0 in the denominator. And by looking at the graph, we can see that, okay, the limit as x approaches 1 of g of x is positive infinity here, and as x approaches 3 from the left, we get negative infinity, and as x approaches 3 from the right, we get positive infinity. And so if we say the limit as x approaches 3 does not exist because those don't agree, but I want you to be able to use that same analytical reasoning in order to arrive at this without looking at the graph. And so when we pick a value such as 1, you put in a 1 in the numerator, you're going to get a negative number. And so you have to decide, what are we going to have, negative or positive, negative or positive? So we have a negative up top. In the bottom, as we approach from the left, we're going to have a negative number, but a negative number that's squared. So that's always going to give us a positive number, whether we put in a negative or a positive number. When we square it, it's still positive. And when we put in a 1, 1 minus 3 gives us a negative 2. Well, we see that these negatives cancel, and so we'll have a positive quantity. And so as this value approaches 0, we know that this whole thing is going to approach infinity. So instead of saying dividing by 0 is undefined, which that's true, dividing by 0 is undefined, but as a denominator approaches 0, our function approaches infinity. And then you just have to decide with the signs, is it positive or negative?